Welcome back to our series of geotechnical engineering. Today we will start our lecture with the topic seepage through soils, that is 2D flow, two-dimensional flow. So flow in water through a permeable medium under gravity is called seepage. Now in 1D flow, in one-dimensional flow, Darcy's law is valid. That is, flow is unidirectional flow. In reality, that is in earthen dams or sheet piles, flow is not unidirectional and velocity is also not constant. So these are the two constraints in the real life. In such cases, quantity of seepage and other parameters are estimated by the help of flow nets. So we will look into the flow nets. First, we need to study some basics. So types of head, there are three kinds of head: velocity head, pressure head, and datum head, or we can say it elevation head. So now the velocity head is found by v square upon 2g. It is neglected in case of seepage analysis because its magnitude will be very less, as the flow is laminar through the soil, so the velocity will be very slow, so the velocity head will be negligible. The second is pressure head. Pressure head is found by P, that is pressure divided by unit weight of water. So it is found by piezometer, by inserting a piezometer at any point of study. The third head is elevation head, represented by Z, and it is found by the distance from the datum to the point of study. So now the total head will be 0, that is velocity head will be neglected, or 0, plus pressure head P by gamma W plus Z, datum head. So we can see the total head, that is water level in a standpipe with reference to datum level. Now head loss. Head loss is difference in total head between 2 points in a soil through which flow is occurring. Now let's come on to flow nets. So patterns of flow lines. Flow lines are those lines which are represented by the psi, and the equipotential lines, those are represented by phi. So the patterns formed by the flow lines and the equipotential lines is called flow net. Solution of Laplace equation for relevant boundary condition gives flow net. Graphical representation of head and direction of seepage at every point is given by flow net. So this is the introduction for the flow net. Now there are certain properties which are related to the flow nets. So let's see the properties one by one. So flow lines, that is psi lines, and equipotential line, that is phi lines, meet each other at 90 degree. Psi and phi lines are smooth continuous curve, either elliptical or parabolic. No flow can be across flow lines. Velocity of flow always 90 degree to the equipotential line. Area bounded between two adjacent psi lines, one psi line is this, another psi line is this, so the area bounded between two adjacent psi lines is called flow channel, Quantity of water flowing through each flow channel is same. Area bounded by two adjacent phi lines, that is, this is the phi line 1, this is the phi line 2. Now this is the psi line 1, this is the psi line 2. So the area bounded to adjacent psi lines and phi lines is called flow field. So this is the flow field. Isotropic medium flow field is square, and in non-isotropic it is rectangular, or we can say it is linear or curvilinear. Now loss of head between two psi lines is called equipotential drop, remains constant for all phi lines, that is the equipotential drop between any two equipotential lines will be constant in a given flow net. Now flow net remains unchanged if boundary conditions are not altered. If the boundary conditions are not altered, the flow net will remain the same, that is for same set of boundary condition flow net is same. So these all are the properties which are related to the flow nets. Now let's come on to applications of flow nets. So flow net is used for determining the seepage, determining the seepage pressure, determining the hydrostatic pressure, and determining the exit gradient. Now the next is determination of seepage. So how seepage is determined? So we know delta Q, that is small flow per unit time flow through each flow channel, is denoted by delta Q. So in isotropic medium, flow field is square, that is B into B. So delta Q is equal to KIA from Darcy's law. K into, at place of I, we wrote delta H upon L into B into 1 because L is equal to B. Then delta Q will be equal to K into delta H. So total head loss is denoted by capital H. Number of potential drop is ND. So the total head drop will be equal to ND into delta H. So our delta Q will be K into H upon ND. Now number of flow channels NF, total flow through the flow net will be equal to Q is equal to delta Q, flow from a flow channel into number of flow channel. So we put these equations here. So our total flow will be equal to K into H upon ND into NF. Now in this equation, look at the ratio of NF by ND. So this NF by ND is called a parameter which is called the shape factor of the flow net. So it is independent of K and H, characteristic of a flow net, and it is called shape factor of a flow net. So we got the formula Q is equal to K into H into NF by ND. Now this was for the isotropic medium. Now for the non-isotropic medium, we know the equation is Kx into del square H upon del X square plus Ky into del square H upon del Y square equal to 0. Now can't be solved, this equation can't be solved, so we have to transform it into Laplacian format. So for that we assume xt is equal to x under root ky upon kx. By this assumption, the equation that was not solvable will convert into a Laplacian format and we can solve it. So it will turn into del square h upon del xt square plus del square h upon del y square equal to 0. So in the actual section, delta qa is equal to kx into delta h upon L into under root kx upon ky into L into 1. Whereas in transformed section, delta qt is equal to ke into delta h upon L into 1, where k is the equivalent permeability coefficient. Now equivalent permeability coefficient, if in case of 2D flow, so it will be kx into ky. Now equivalent permeability coefficient if it is case of 3D flow, so kx into ky into kz and cube root of this. So by this we can find the equivalent coefficient of permeability. So we get here for non-isotropic medium, delta q is equal to ke into h into nf by nd. Now second is determination of seepage pressure. So if nd is number of potential drop, delta h is head drop every time, and h is the total head causing the flow, so the net head available at point of study is h1, that will be equal to the overall head and the drop that happened till the point of study, that is nd into delta h. So this will be the head at the point of study, which is given here. Now seepage pressure ps, now the seepage pressure will be equal to h1, head at the point of study, into unit weight of water. So that will be the seepage pressure at the point of study. Now we know that h1 is h into h minus nd into delta h, and that multiplied by unit weight of water gives us the seepage pressure. So the seepage pressure acts in the direction of flow. We have to remember this. Seepage pressure acts in the direction of flow. Now determination of uplift pressure. So hydrostatic pressure at any point after nd potential drop is given as U equal to HW into gamma W. So HW is what? HW is the head at that point. So HW is equal to H1 plus minus Z. So HW is the piezometric head at the point. Now determination of exit gradient. So hydraulic gradient at downstream side of flow, where percolating water leaves soil mass and emerge out as free water. So at the downstream side, the seepage pressure tries to comes out at this junction, where it tries to comes out as free flow. At this junction, the gradient is called exit gradient, which is given by IE equal to delta H upon L, where delta H is the head drop at every time, and L is the length of smallest square in the last flow field, and delta H is the drop. Now, seepage pressure. So, water flow through saturated soil mass, it exerts pressure on soil solids by virtue of its viscous force. So, when water flows through the soil mass, it exerts a pressure on these soil grains. This pressure is called the seepage pressure. So, this pressure is seepage pressure, denoted by small p subscript s. Now, Ps is equal to H into gamma W, where H is the head causing the flow. So seepage pressure will be equal to, at place of H we will put up the value, so I into Z into gamma W, this will be the seepage pressure. Now area of the cross section is A, so area into this, area into pressure, what will it give? Seepage force. So seepage force will be, now we have this area and this depth Z, so area into depth will be volume. So the seepage force will be I, means hydraulic gradient, into unit weight of water into volume of the soil specimen will give us the seepage force. Now the vertical effective stress. Now we know that there is a total stress acting on the particles. This total stress is sum of effective stress that is acting on the particle plus the pore water pressure. So these are the soil grains, this is the water, so this water exerts some pressure, so this is pore water pressure, and there is also a certain effective stress on the grains, so sum of this will give the total stress. So we have to represent it as a equation that is denoted by the effective stress is equal to total stress plus minus pore water pressure. So there are three kinds of flow condition, that is no flow, that is water is static, second is downward flow condition, and the third is upward flow condition. So we have to remember the conclusion that if there is happening downward flow, then the pressure head is decreased by Iz, and the pore water pressure is decreased by Iz gamma W at any point of study. Similarly, in upward flow condition, pressure head is increased by Iz and the pore water pressure is increased by Iz gamma W at any point of study. So this is the conclusion that we have to remember. Now the next topic is quicksand. So what do you mean by quicksand? So quicksand is upward flow condition when the soil is in submerged state, effective stress gets 0. So this is the upward flow condition when soil is in submerged state and the effective stress on the soil particles gets 0. Cohesionless soil loses its shear strength, so the particles loses its shear strength, effective stress on these are 0, so this particle gets to the surface like it is free floating. So this condition is called quicksand. So the effective stress is given by delta is given by sigma bar is equal to sigma, that is total stress into pore water pressure. Now we are saying the effective stress on the particle becoming 0, so this will equal to 0. Now total stress here will be the soil mass is wholly submerged into the water. So for this soil mass, the total stress will be gamma submerged, unit weight in submerged condition, into the depth of the soil Z minus the pore water pressure. Pore water pressure will be I Z, the depth of the soil mass, into gamma W. So this equation will equate to 0. So from here we will get gamma submerged into Z equal to I Z gamma W. So Z will be cancelled. Now we will remaining with I is equal to gamma submerged upon gamma W. Now this ratio gives us a gradient, hydraulic gradient, and this hydraulic gradient will cause this condition where effective stress will get 0. So this is why this hydraulic gradient is called critical hydraulic gradient. If this hydraulic gradient exists, then the quicksand condition will start happening. So it is denoted by IC. So IC is equal to gamma submerged upon gamma W. Now if we use the SE equal to WG formula and rearrange the terms, we will get another formula, that is IC is equal to G minus 1 upon 1 plus E. So G minus 1 upon 1 plus E will give us the critical hydraulic gradient for causing the quicksand condition. Now for fine sands and silts, the value of the specific gravity is around 2.65, whereas the value of E, void ratio, is around 0.65 generally. So for fine sands and silts, the critical hydraulic gradient's value will be near about 1. Now when such condition occurs below hydraulic structures, piping occurs. Suppose there is a hydraulic structure and there was seepage happening. Now in this seepage, if the soil mass in this zone gets into quicksand condition, So slowly the particles will start to float in this zone. Now if they are floating, so with the exiting water, the soil particles will also exit. So after some time, this section will become hollow like a pipe, and due to this, the bearing capacity of this much soil mass will reduce. It can't bear the load of the hydraulic structure, and certainly it will fail after some time. So due to this kind of condition, this kind of behavior is called piping failure. So when such condition occurs below hydraulic structures, piping occurs. So to be safe against it, we take a factor of safety, that is critical hydraulic gradient is equal to factor of safety into the existing hydraulic gradient. So this FOS will give us safety against the quicksand condition. Now quicksand condition generally occurs when excavation is done below the groundwater table. Suppose this is a ground. Now the groundwater table is this. Now if we start excavating and we reach below the groundwater table, and we keep pumping out the water that is seeped into the dug hole. Now if this continues for a time, then suddenly the particles on the side of this dug hole will start to free float, as the effective stress on them will be 0. So suddenly the collapse will happen. So in this case, the quicksand condition will happen. So quicksand condition generally occurs when the excavation is done below the groundwater table and water pumped out to keep the excavated area free from it. Also when sand is under artesian pressure below clay layer. So if there is a clay layer, and below it is a sandy strata which is acting as a artesian aquifer. Now if the pressure is more, so suddenly the effective stress over this sandy soils particles will become 0. So again the quicksand condition will occur in this zone. Now flow through non-homogeneous section. So change in soil conditions, flow lines deflected at interface with permeability K1 and K2. So here you are looking that here we have one soil mass and here we have a different kind of soil mass. Now this is the interface of both of the soil mass. So now if we draw a straight line at the junction, so this is the alpha 1 angle and this is the alpha 2 angle. Now these are the flow lines. So the concept says change in soil condition, flow lines deflected at interface in such a way that K1 upon tan alpha 1 will be equal to K2 upon tan alpha 2. Now K1 and K2 are the coefficient of permeability of both the soil. It says that if K1 is greater than K2, the K1 is greater than K2, then the flow lines deflected towards the normal. So the flow lines will deflect towards the normal. Now if the K2 is greater than K1, then the flow lines will deflect away from the. Now if in case K2 is greater than K1, then the alpha 2 will greater than alpha 1. So in that case the flow lines will deflected away from the normal, not this way. They will go like this. The angle will keep increasing. Now we have discussed already the piping failure, so here we look into it in depth. So the piping failure and its protection. Governing criteria is exit gradient. So to be safe against the piping failure, we have to know the exit gradient. When exit gradient IE reaches critical hydraulic gradient, that is IC, then boiling condition occurs. Boiling condition means on the soil particles the effective stress is 0, so they start coming to the surface like they are boiling molecules of water. So this is why that condition is called boiling condition, which leads to erosion of soil mass. Now if these soil particles comes to the surface, certainly with the flow of water they get washed out, certainly this region after a time will become hollow. So the soil erosion is happening. So boiling condition occurs, which leads to erosion of soil. Such soil erosion creates a pipe shaped discharge channel that we have discussed, that the soil mass will get eroded over time. Now this section will become hollow like a pipe structure. So this flow channel will get hollow. With time, width of I of channel. So with time, the width and I. So with the time, if this pipe was this much, now with the time this will keep growing, and the soil above it can't hold the weight of the hydraulic structure and it will collapse. So that is called piping failure. So with the time, width and I hydraulic gradient of the channel will increase, leads to the failure of structure. This kind of failure is called piping failure. So for fine sand there will be no piping if we keep the exit gradient in the range of 1 by 5 to 1 by 6. In case of coarse sand, there will be no piping if we keep the exit gradient in the range of 1 by 5 to 1 by 4. So this we can take as precaution to avoid the piping condition. Now methods of preventing piping. So first is sheet pile, that if there is a hydraulic structure, so we can provide sheet pile. Generally it is given at the downstream side, so that the water that is coming from the seepage will have to move a longer path, so it will lose its energy, its head, and so the loss of head will be more, so the exit gradient will be very less, so this water will not have enough potential in it to erode the soil mass. Similarly, these sheet piles can be provided also on the upstream side of the hydraulic structure, upstream side, and also on the downstream side. So overall the water has to travel a larger path, so it will lose its most of the head, that is its energy, so it will not cause us the piping failure. Second is the inverted filter. So at the downstream side we provide a permeable medium, that is drainage filter, a filter kind of thing which attracts this seepage water. So the seepage water, instead of going anywhere else, it attracted towards this filter and it comes into it, and because this filter is permeable, its permeability is good, so the water comes only from this place, and at this place we can provide some piping or some arrangements which can drain out this water safely without causing the piping failure. So seepage through earthen dams, first is drainage filter provided, second is drainage filter not provided. There are two conditions in the earthen dam. So when the drainage filter is provided, so this is the hydraulic structure, this is the drainage filter. Now look at here, the drainage filter is this. Now this point of the drainage filter is called F. Now from here if we draw a curve straight, so the point which we get here is D, and this D is at 0.3 times of L. The L is the distance of the point. If we connect this A point to the top surface of water, then we get C. This B to C distance is called A, and at 0.3 times of this L there will be a point D which we have to connect to the end of the seepage filter. So the seepage will happen like this, it will go to the center of the seepage filter. In this condition, the S, that is the length of the seepage filter, the length of the seepage filter that we have to give is S. So in this condition we can compute the length of the seepage filter as S is equal to, in bracket, under root D square. Now what is this D? So D is the distance of the point D from the point F. So the distance between the F and the D point is called D. So the D square plus H square. Now H is the total head at the upstream side. Now under root of this minus D. So this will give us the length of the seepage filter that we should provide to prevent the piping. Also we have already discussed that in the case of 2D, the equivalent K value will be found by Kx into Ky whole power 1 by 2, and in case of 3D, Kx into Ky into Kz whole power 1 by 3. Now the second condition is when drainage filter is not given. So in this condition, the flow will happen like this, like this way, and the sieved water will come out from this point, and this point is at a distance of A from the toe of the hydraulic structure, and the angle made by the slope of the hydraulic structure is alpha. So we can find this A distance. We have to find this A distance, like at what height the seepage water will discharge out on the downstream side. So in this condition, if the alpha is less than 30 degree, then the flow of the seepage can be found by K into A into sine alpha into tan alpha. Also A can be found out by D upon cos alpha minus under root D square upon cos square alpha minus H upon sine square alpha. So by this we can find that A distance. Second case, if the value of alpha is between 30 to 60 degree, so in this case the seepage flow will be Q K into A into sine square alpha, and the value of A will be equal to under root D square plus H square minus under root D square minus H square cot square alpha. Now in this case the values of the B and the D will change, like we have to see. In this case, when drainage filter is not provided, so the F point will be here. So from this point to the point D, the distance will be D, and B is the distance of the F point to the A point. Now the next topic is flow net diagram, how to read it. So if you have a flow net diagram like this, so in this we can count like how many flow channels are there. So there are 1, 2 and 3. So there are 3 flow channels, 1, 2 and 3. So the value of the NF will be 3. Now how many ND like potential drops are there? So we have to count it like we have to look at these lines first, and on basis of these we can count like 1, 2 and 3, 4, 5, 6, 7, 8, 9 and 10. So there will be 10 potential drops in this flow net. The head will be this, H is 6 meter, and the head at any point is found by H minus ND into delta H. So by finding the head at every point, like at A, B, C, D, we can, A, B, C, D are the points, like A is here, B is here, C here, D, E, F. So by finding the head at the A, B, C, D, we can find their values and make a diagram. Like at A the uplift pressure is 67, at B the uplift pressure is 43. Similarly for every point we get a curve. This curve is called uplift pressure distribution curve. So that's all for this video. In this video we have discussed about the flow net, its properties, and the piping failure, the quicksand condition. Thanks for watching.